Well, good afternoon, folks. Good morning, whichever time zone you are in. Welcome to today's webinar in our Synerzip monthly webinar series. I am your host today, Hemant Alhans. And the topic today we're going to cover is Blockchain Application Development 101. And given the number of registrations we have for this webinar, looks like this is a very popular topic and a lot of you have huge interest in digging a little deeper. So many of you have heard about this topic of blockchain, and from many descriptions I have seen, this has a promise of being as groundbreaking as what TCP/IP was for communication and internet a couple decades ago, or what some people have described double entry accounting system was a couple hundred years ago. So let's see how this actually pans out. So what we'll do today is we'll dig deeper into building real world software applications following the blockchain mechanism or the construct. In today's session, we'll cover the basics of what class of business problems lend themselves for using blockchain and how to appropriately model them to leverage blockchain construct, and what are these things called smart contracts, distributed ledger, or cryptocurrency. All these things we'll clarify. And then you may have heard of the alternative technology platforms like Hyperledger or Ethereum and so on. We'll cover those and so on. And we have with us two seasoned engineering leaders who are actually building blockchain-based software applications. So I'm delighted to have, and I'll introduce the speakers in a minute. Let me first cover the logistics for us today. The logistics-wise, we'll have about 45 minutes or so for this session for building blockchain software applications 101. And I'll take some questions as a moderator. You guys as the audience, feel free to send in your questions. If anything is not clear, I'll keep track of questions and I'll bring those questions up to our speakers today. And then we'll still hopefully have another 10 or 15 minutes towards the end to take any broader, bigger questions that didn't get covered along the flow. So that's the general pattern, and after the webinar, we will make the recording of this webinar available as well as the document that we use, the PowerPoint or the PDF version of it. That's the general plan. With that, let me introduce our speakers. We have Glenn Jones and Ken Staker. Both are seasoned software executives, engineering leaders. They have actually built software applications, many of them, and in this case, they're both leading blockchain application development work at Sweetbridge, which is a partner company for Synerzip, and we'll cover a little bit more of that towards the end of this session. With that, over to you, Glenn and Ken, to cover this topic with us.
All right. Thanks, Hemant, and I appreciate the introduction. Make sure everybody can hear me. So I'm going to spend a few minutes here talking about and kind of level setting on what blockchain is. And as Hemant said, Ken and I have been working in blockchain for well over a year, building, and we're taking blockchain and leveraging it to build out supply chain applications. But to start out with, what is a blockchain? And so you've heard the term distributed ledger technology, or DLT. It supports peer-to-peer trading. I'll go over some of the different types of blockchains in a minute, but the common thing between different types of blockchains is the idea of consensus and being able to accept transactions, validate transactions through a consensus model. And what exactly does that mean? So, hopefully you're familiar with Bitcoin and some of the other cryptocurrencies out there on the market, Bitcoin being the first one on the market. And so what happens is when someone wants to transfer Bitcoin from one person to another, and by the way, this is autonomous, then they use an application to send a request into the blockchain. That request goes in, and it goes into a many nodes. And so in the case of Bitcoin and Ethereum, these nodes are independent companies. They're called mining companies. That's a generic term for them. And they work in a way through cryptographics to validate a transaction through a consensus model. And there's a few different types of consensus models we'll talk about in a minute. But as that transaction gets validated and it's verified through these consensus models, it's then put into a block. And the block is added to all the other blocks in the blockchain. And for example, I believe Bitcoin, there's a new block added every 10 seconds. And so every 10 seconds, a set of transactions are added into the block, and that is what completes the transaction. And so it's a highly, what's called decentralized system. These nodes are decentralized or independent, and it takes a significant amount of computing power to be able to do the verification of a block. So what are blockchains good for? This is kind of a long word, immutability, which means storing a transaction. And once you put a transaction into the blockchain, it's there for posterity. It's there forever. And most blockchains, at least public blockchains, are visible. So anyone who has access to the blockchain can see that transaction. They can see that there's 10,000 Bitcoin in this account and 5,000 Bitcoin in this other account. And they can see over time how that Bitcoin has accumulated, or Ether in the form of in Ethereum. And so it's what they do is it's a digital representation of these different entities, and it logs all the state changes. So it's like a log on a database. I mean, that's kind of one way of looking at it. And what are the different types of applications? Again, transactional type applications. By far the most popular is cryptocurrencies, which is essentially a store of value. And what a store of value is, it's a function of an asset that can be saved and retrieved and exchanged at a later time. And it's very predictable. And so money, currencies, commodities like precious metals, gold, these are all stores of value. And so again, back to it's a transactional type system. Identity management is another great application for blockchain. In other words, who are you? Where did you come from? What is your provenance over time? Potentially, what is your credit rating? And this would be more private, but it's a way to store that and store the evolution of your identity and how you've evolved over time. Another great example is a digital representation of some asset, like a vehicle, a car, or a bus, or a truck. And we call that tokenization. So what you're doing is you're building a token that essentially the same thing as a coin to represent that asset. And you can lock that asset, and one of the things we do is we can lock an asset like a vehicle, and then you can take a loan against that vehicle using cryptocurrency. So you can see, who owns the asset potentially if the blockchain is set up to show who the owners are. Another great example is, and one thing that we work on is tracking provenance of a food or a drug. So as a source, a supply is manufactured, that can be logged on a blockchain. As it progresses through the supply chain, every step through the supply chain, it can be logged on a blockchain, and you can look back and you can see what is the provenance of that particular food, drug, or other type of asset. So these are all great examples of different uses for blockchains. Blockchains are not good for executing AI algorithms or running AI, running complex planning and scheduling algorithms, real-time type control. They're fundamentally transactional systems. They're not really designed well to support the big data or denormalization or running heavy-duty algorithms. And what part of it is because of the consensus model, the miners or the companies that do the processing, they charge fees for it. And so it's not good for process-intensive applications such as these algorithms. What is the evolution of a blockchain? So blockchains have evolved. The first generation, which was Bitcoin, was designed and put into production in, I think, 2009. And so that was almost 10 years ago, 9 years ago. And it was the original store and transfer. Satoshi Nakamoto was the white paper described how the blockchain would work. But first blockchain, Bitcoin, was designed specifically to handle Bitcoin and not be able to do much of anything else. Companies forked, so it's open source, companies forked Bitcoin, and they were able to create other currencies based on that with different kinds of, maybe a few different types of attributes, so Dash and Ripple, for examples. Second generation blockchains are programmable now. So instead of being static or having to fork the blockchain to make it do something special, the next generation of blockchains, like Ethereum, for example, are now programmable. They have a programming language. They have a virtual machine, typically, that will run programs. A great example of this is Ethereum. Ethereum was launched in 2013. So, you know, quite a bit of time between the initial launch and then the programmable blockchain. Third generation blockchains are enterprise blockchains. These are blockchains that don't run in the more traditional consensus model where you have miners and highly decentralized. In typical enterprise blockchains, you know who are the members and which members of the economy or the system are actually running the consensus model. So it's known, and the advantage of that is you can build much faster transactions, and you can run applications much quicker on these enterprise blockchains. But it is still distributed, and so it's a distributed ledger. Examples of this are Hyperledger, which is probably one of those popular ones, and Ken will talk about that in a minute. R3 Corda, and Ethereum actually has a Enterprise Ethereum Alliance. JP Morgan is kind of sponsoring and building out this Ethereum Quorum, which is a enterprise version of the Ethereum blockchain.
Hey, Glenn, can you take one question?
Sure.
Now covered a couple of key concepts here. Can you clarify this notion of distributed ledger versus smart contracts? Are these alternative ways of leveraging blockchain, or these are always there in every blockchain, the notion of smart contracts or distributed ledger?
So they're complementary. They go with each other. So a smart contract leverages the ledger to record transactions. And so in the second generation, these smart contracts were introduced as the programmable part of blockchains. And so the actual smart contracts are distributed just like the transactions are, and they're validated just like transactions. So essentially the programs themselves are treated like transactions as they're distributed. That answer your question, Hema?
Yeah, that sounds good. Thanks.
Sure. So the current set of blockchains are even the enterprise blockchains. I mean, they're still in what I would consider early phases of supporting the kind of scalability that a MasterCard or American Express, or that support like microtransactions, or like SAP and Oracle in the case of enterprise blockchains and those kind of finance systems. So the next generation of blockchains are highly focused on scalability, highly focused on through concurrency. So we track several of these. A good example is Archain. They will release sometime in 2019, I believe. And most of these other initiatives, IOTA and companies like that, are positioning in that time frame also in the next year. So the challenges with the current generation of blockchain is scalability and also the cost of running them. The Ethereum, the price for transactions in Ethereum have gone up significantly over the last year, which makes it very difficult or challenging from a cost perspective to put more complex applications on Ethereum. Maybe not so true for Hyperledger.
Glenn, sorry to come back to that. Maybe for the audience, can you just simply describe the smart contract? A lot of people don't know.
Yeah, can I do that in a few slides? I've
Sure,
got another slide coming up where I'll describe in more detail what a smart contract is.
Okay, sounds good.
So next thing I want to talk about is the permissionless versus permission blockchains. And it's a really important concept because when you're designing systems, you have to make a kind of a conscious decision. Do you want to design for a permissioned blockchain or a permissionless blockchain? Permissionless means anybody can participate. So any of you can download a Ethereum instance from Parity or Ethereum, and you can run it, and you can collect all the blocks. You need a fair amount of disk space. I forget, we're up to about 4 or 5 gig, I think, is what the current block count is. But anyone can download this, and you could become a miner. Except you need now that we're in 2018, and the cost of mining and creating transactions has gone up significantly. So these are decentralized. Anybody can enter the market. Anybody can build a mining camp, and so there's no real control over who does the mining, but whoever does it the fastest gets the gas rewards. And so the compensation comes through what they call gas in Ethereum, and it's fees in Bitcoin. And so if a miner is able to deliver a consensus or a result the fastest, they get the most fee. And this happens for each one of the blocks. So that's what permissionless is. Anybody can enter the economy. The permissioned is more of a federated model. It's where everyone in the environment or economy is trusted, and that means that, for example, in the case if you had a supply chain as an example, and you have Hewlett-Packard, and you have Seagate, and you have Best Buy, and each one of those were participating in providing a node in the blockchain. If Western Digital wanted to enter the blockchain, they would have to get permission. There's different ways of doing that, but they would have to get permission to get into the blockchain, and they would be accepted in the blockchain. The advantage of this is you can build much leaner validation models that don't require the level of processing, so the transactions run significantly faster, and you can also put more complex processing and more complex models into the blockchain. So that's kind of the trade-off, and it's important to kind of understand that if you're going to develop open applications that are trustless, then you would need to use a permissionless and use a Ethereum type model. If you're developing for an enterprise where you need to protect certain kinds of data, then you want to develop on a Hyperledger or a permissioned blockchain. So I'm going to give an example now. I'm going to spend a few minutes and go over sort of how Ethereum works and how Ethereum smart contracts work, and then Ken's going to take a few minutes and go over how Hyperledger and Hyperledger smart contracts work. So Ethereum, one of the things you'll hear is a Dapp, or a decentralized application. And essentially what this is if you look in the world of Ethereum, there's a decentralized block chains, which is shown in the blue, the different blockchains of Ethereum, and they're ran by the miners. It's the consensus is called a proof of work. What that means is that a miner has to go through and apply the cryptographics to all of the blocks in the blockchain, and then in order to get consensus. And several of them have to do that in order to accept a transaction. And like I said, a smart contract is a transaction. And so a smart contract is code. And I'll show you an example of the code in a minute and what that looks like and how it is pushed into the blockchain. So to get into the blockchain, like I said, anybody can download an Ethereum node and can run it and can collect all the blocks and can take new transactions in. So typically what we do is we have like either an instance or we use Infura, which is a consensus company that runs in Amazon, that we connect into an Infura instance, and then we interact with the global blockchain using Infura. And again, it's just another a node in the blockchain, but it's not nearly as powerful as the ones that actually do the consensus nodes. There's several instances out there. There's a Geth, which is a Go instance. Their Parity builds, I think, a Rust, I believe is what they developed in. There's a C++ instance. There's a Python instance. So you can download. These are all open source, and you can download and run them. And then one way to do an application is purely do everything in a web UI. And so, or in a mobile application. So there's no, other kind of database. You're using the blockchain purely as your database, and this is what's called a distributed application, or a Dapp. We tend to write these in React and JavaScript. JavaScript has a very strong, interface. They built a library called Web3.js. Web3.js it abstracts the whole interface into the blockchain. It lets you access all the server side, so you can think of smart contracts as kind of the server side application, and you think of the Web3.js and the Node.js as the client side of the application. And then the Web3.js is the way that the React or JavaScript or Java on a smartphone, Android, that's the way that they interact, and it runs through JSON, or typical REST type call, JSON over HTTP. And this works for a lot of the apps. If you go look at CryptoKitties, if you're familiar with that one, that's one of the new ones on Ethereum that's been taking a lot of bandwidth, but it's designed in this way to where you can interact, and there's no other database, there's no other system. More complex applications have to use a different approach, and this is what exchanges. So if you go out to exchanges like Poloniex or GDAX, or if you're trading cryptocurrencies, these things run more in a SaaS mode, and our applications are having to do the same thing. And so what this does now, you've complemented the blockchain now with other more of a, what I would call a software as a service type environment. We tend to run in Amazon, or you can run in Azure or one of the other cloud systems. And we build out Node.js using Docker or Lambda, again, using the same library that can interact through Infura and get access to the smart contracts. And again, I'll just say, the smart contracts, and I'll talk about this more in a minute, but they're kind of like a stored procedure or something like that that can do processing. So we have this. If you write in Go, or you're writing more complex algorithms, there's a Web3.j that gives you a Java interface. There's a Go interface. So Ethereum puts out a whole set of interfaces or APIs that they're libraries that you basically build into your application, either compile in or join at link time or at runtime, that give you access back. And Amazon has a great environment for building these things out really quickly. Then you can have a different persistent store for other kinds of data. Like I said, anything you put in Ethereum, everybody in the world can see it. So you would never put someone's social security number or some kind of personal information in there. All of that needs to be stored on an external database. We go through in our applications, we have a membership app, which all of our members of our economy go through a KYC AML process, know your customer, anti-money laundering. So we vet everybody. So we ask everyone who applies for our application to fill out an application that includes private information. And we store all that private information on a private store that's highly secure. And then we store transactions back through smart contracts on the blockchain itself. So that's, whenever you're modeling and designing systems, it's really important to understand, especially if you're using these permissionless type nodes like Ethereum. You have to be very conscious about what you put on the blockchain versus what you don't want to put on the blockchain. And so you need a totally encompassing solution. So let's talk about smart contracts for a second. In Ethereum, it has a virtual machine. So it's similar to a Java virtual machine. It has an assembly language that you can write in, that you can go right down to the node level, and you can go down and write against if you're trying to optimize for performance. But you can also write in higher level languages. And so again, a smart contract is very similar to a stored procedure in a regular database. To that fact, when I think about blockchains or as an architect, you think about it like it's a special type of database. It's a special type with a programming language. So it's like we use MongoDB, we use Postgres, and we use blockchain. And so in blockchain, you put certain kinds of data in and you make decisions around what kind of data you want to put in there and what kind of processing you want to put in there, hence the smart contracts. Same thing with MongoDB. You put documents in MongoDB. You wouldn't necessarily put relational data in MongoDB. You can do it, but it's not built for that. In a relational database, you tend to put relational database data. So smart contracts, by far the most popular language on Ethereum is Solidity. It is a Turing complete language. It's very similar to JavaScript. It was designed in a way it's like the JavaScript developers could pick it up very quickly. For that fact, you'll see a theme across most blockchains today. They really embrace JavaScript developers. There's a tremendous number of developers out there that know JavaScript, and so, but the challenge is in blockchains, especially like Ethereum, you're typically building fintech type applications which have which are dealing with millions or even billions of dollars worth of coin, tokens or Ethereum. And so you have to build these applications to where they're highly secure. And so so you want to typically when you're building applications like that, you want a tightly scripted type language. And so that's what Solidity provides on top of JavaScript. It's more like a TypeScript. So you have a strongly typed language. And I've just put an example in here. You know, it supports address as a first-class citizen in Ethereum. So an address can be the address of a smart contract, or it can be the address of just a ledger. And then the mappings it's like a hash map. And so they support, you know, more advanced functions. Solidity, while it's mainly a structured programming language, it also has inheritance. So it has a few aspects of an object language, but I think most people would say it's built more as a structured language. And it's done because, again, you want to have an implementation that is highly secure, and I'll go over some of the testing methods in a minute. Serpent, on the other hand, is another language that runs and compiles into the same EVM, just like you know, you have other languages that compile and run on top of the Java virtual machine. Serpent is another language that goes on top of the Ethereum virtual machine. Serpent is designed for Python programmers. So if you're a Python programmer as opposed to a JavaScript programmer, you might want to use Serpent. Serpent's not quite as powerful as Solidity is, but it's certainly, if you're just trying to do something quick and you're used to Python, you can pick up Serpent very quickly. So let's see. So talking about how do you deploy a smart contract? And so I've shown here kind of the Dapp example of how you deploy. And so you have a front end running in JavaScript, a web UI maybe, and then you have a Solidity contract that you have in that UI that you want to deploy down into Ethereum. And so the first thing you have to do is compile. So you have to compile it down into the bytecode so you can send it through Web3.js into the Solidity compiler, and you can get the resultant executable back. And then the next thing you have to do, a key thing to deploying into the Ethereum or into any blockchain, is having a private key. And so this private key it's always located on the client. You never move a private key across a network. It is used to encrypt or to do a hash on the transaction itself. And so you apply that private key using Web3.js, and it pushes onto the Ethereum node, and then the Ethereum node can then deploy that down through one of these clients into the Ethereum network. So, it posts it and then it returns the address. So once you post a smart contract, you get an address back, and that address is public. You can post it anywhere. You can put it on Facebook, or anybody can go query it and they can see what that smart contract is. They can also see the bytecode for that smart contract. So all that's in public display. They can, if you have a bug in your code and you deploy a smart contract, somebody else will typically look at that smart contract and maybe if they're nice, send you a note. If they're not nice, they will exploit your bug and potentially steal your coins. So you have to be really careful, and I'll go through the process we go through to validate and vet these smart contracts. So I just wanted to give you a feel for how that works. So what are some of the challenges with Ethereum? The first and foremost is security. I mean, again, you're storing, or at least we will wind up storing hundreds of millions or billions of dollars in our under the control of our smart contracts. And so you have to have a process for making sure that the data is protected. And so part of the security is how do you manage private keys? And like I said, you really never want to send a private key across a network. So whenever you're building your client, your web application or your mobile application, you have to have a clean way to store and be able to retrieve private keys. There's different standing technologies and ways of doing that. One of them is called a key store file. Other ones are just to store it locally. So the other thing to be really careful of when you're designing smart contracts is minimizing what we call attack vectors. And what that means is you want, to minimize the number of APIs to actually minimize the amount of code that is in a smart contract. So the code does a very specific thing and it does it well, and you can have third parties come in and audit that code and said, yes, it does what you say it's supposed to do, and I'll go over kind of the process we go through to have third parties in a minute. The other challenge is transaction latency, and cost. And I mentioned the cost of running transactions a few minutes ago. It continues to go up over time. Latency is around whenever you submit a transaction. Let's say I'm going to send a Ether from myself to Ken, and so whenever I submit the transaction to send Ken 10 Ether, I will package that up. My application will package it up and it'll submit it to the blockchain. Depending upon how much gas is the fee. So how much fee I spend, I can get that transaction to run faster. So if I want to send 10 Ether and I want to spend a half an Ether on the transaction, that transaction will probably get mined in the very next block, which means Ken will get his 10 Ether very quickly. If I'm going to be, I can also say I'm going to spend a tenth of that amount on fees, and it may take a week for the transaction to go through. So, you can trade off cost with performance, but every single month, the cost of Ethereum and doing a transaction on Ethereum goes up. Executing a smart contract is the same way. The smart contract is a set of instructions. Every single instruction costs Ether. And so if you write a big smart contract and you deploy it, it's going to cost money to run. There is a limit to the amount of money. So if, for example, if you get in an infinite loop for some reason and you have it deployed, then it'll still spin the Ether. You don't ever get the Ether back, but it will stop. It'll cancel your transaction. So you also have to watch how long your transactions or how long your smart contracts run. The other thing, Ethereum is its solidity, or actually the EVM is all integer. So it's all integer programming. There's no floating point. But as you know, whenever you're trading Ether, for example, Ether's up. It was up over $1,000. Now it's back down to maybe $400. But you want to be able to trade fractional Ether. So you still use integer programming, but you have to, your application has to take into consideration the decimal points. Typically, Ether is transferred. It has 18 significant digits, and that's pretty much a standard right now. So 18 decimal places. The last thing talk about on the challenges is the testing. And Ethereum, you have to test, and like any other product, they have test networks. And so there's several out there. There's one called Ropstein, there's Kovan, Rinkeby. Each one of the test networks behaves a little bit differently, so you have to be kind of conscious about what you're trying to achieve during your testing as to whether you want to select which one of these. Typically, newer versions of Ethereum are deployed on, I believe it's Ropstein. So if you want to test on the newest version of Ethereum as it's getting ready to release, sort of in a beta, then you wind up, going on Ropstein, and then Kovan and Rinkeby tend to be, earlier versions. So, but you test very similar to the way you run in production. I mean, but instead of pointing at a production node called mainnet, you point at one of these test nets. Some of the tools we use.
Glenn,
Sure.
Before you move to the tools page, can you, there's a couple more questions coming back on the smart contracts. I wonder if you can maybe use a real world example of application of a smart contract, how the real world kind of a construct would map to what is being called smart contract here. Any way to clarify?
Sure. Yeah, let me take a coin smart contract. So so in the world of Ethereum, you can build your own coin, and you see all kinds of coins out there on the market. There's DAI, there's NEM, there's a ton of, they're called ERC20 tokens. They apply to they support a standard API for doing transfers and getting balances and things like that, but you can add additional functionality to it. So one of the things that we do is we will lock up an asset, and so we will make it to where a user still has access and can see that asset, that token, but they can't trade it, because maybe they borrowed against it. So let's say that we've taken Ether and we put it into a state to where we're borrowing against it. And so when you do that, the smart contract, what it does, it says, okay, here's 1,000 Ether. We're going to lock it up and we're going to borrow just like you would from a house, just like a mortgage. And so whenever you do a mortgage, the lending company takes essentially the title to the house, and you don't really have the title until you've paid off the mortgage. We do the exact same thing. We'll take that Ether in the smart contract and we will lock it up, and that smart contract we use Bridgecoin as the loan, so it'll loan, and until you pay back that loan, it will not release the Ether. You can still see it, and maybe if you pay down some of the loan, you can take back part of the Ether that you put in there, but until you pay back the whole loan, you can't take out all of the Ether. So just as you can't get possession of your house until you've paid off your loan for your house. So that's an example of how, one of the ways that we use a smart contract to lock up an asset. And the reason we do that is we want it to be transparent, so everyone can see it. The other thing is, if you default on your loan, if you don't pay back, the interest or whatever, then the smart contract allows the Sweetbridge economy to take that Ether and pay off the loan. So that's an example of one of the examples of how we use it. So what it does is it gives different kinds of permissions based upon the state of the loan. And so there's a lot of other ones out there that you can look. There's most all the smart contracts, by the way, they're all open source. So if you go look at in Ethereum, you can see pointers to different projects, and most of the projects, if you go into GitHub, and ours is the same way, you can see the source code of the smart contracts. It's part of a way that you ensure security. It sounds kind of funny, but by exposing it, people tend to reply and say, hey, here's a gap in the code, and I'll talk more about that in a few minutes. Does that help?
Great. Yeah, that helps. Great. Thank you.
Sure.
Yeah.
So some of the tools you'll want to know, but probably by far one of the most popular ones is put out by the Ethereum Foundation is Truffle. That's, the tool that you can use to test and to deploy smart contracts. You can use any editor to develop them, but Truffle has a compiler in it, so you can compile, you can check syntax. Dapp another really popular one. It supports both Solidity, but it also supports bytecode development. So you can go down to more of the assembly language in Dapp. I mentioned Web3.js and Web3.j and the other libraries that front end, the client libraries, and those are really important. You need to get, they're a little quirky about how they work, but once you get to know the APIs and how to use them, those things are invaluable. And then I've also included a link in here to probably one of the more popular Ethereum development tutorials. So so Ken will spend a few minutes and talk about Hyperledger. Ken?
Very good. Thanks, Glenn. Can you hear me? I guess everyone can hear me okay.
Perfect.
So I'm going to talk a little bit about Hyperledger as we go into this. And thanks to Glenn for that review of blockchain and Ethereum. It's been great to work with Glenn. He's obviously a wealth of knowledge, and it's been great to learn from him. As we start to talk about Hyperledger, you may ask yourself, are these guys talking about the same technology? Glenn talked a little bit about the difference between public and permissioned blockchains. Hyperledger, we're going to focus more on the permissioned side of blockchain, and you'll see even though the underlying technologies, there's some of the same constructs and concepts, the implementation of those is very different. Just a quick background, I come from a background of 20 plus years of working in a large enterprise on ERP systems, so SAP primarily, and have worked a lot with interfacing between SAP systems and getting enterprise systems to talk to each other. As I started to learn about blockchain and the technology that was available, some of the problems that have plagued ERP implementations and environments for many years, you can start to see really creative and innovative solutions. And to me, that's where I get really excited about blockchain, to see the power that it brings to some of these problems that we struggled with for many years. So as you look at Hyperledger, some of the problems that Hyperledger is trying to address, first of all, is enterprise scalability. Glenn talked a little bit about the public blockchains and the consensus algorithms, primarily the proof of work consensus. Those consensus algorithms are built purposely to take time and to take processing power. And the reasoning behind that is to disincent bad actors. It makes it more economically feasible to participate the way it's intended than it is to try to hack the system. But those algorithms put a level of computational intensity that don't really work and don't really scale in an enterprise environment. So Hyperledger is focused on how do we build blockchains that will scale to the enterprise. Glenn also mentioned how in a public blockchain, the contracts are they're very often open source, and everyone that subscribes to the blockchain can see all the transactions. Well, in an enterprise environment, there are often times when companies will have private agreements between themselves where you don't want to expose that information. I may sell product to different marketplaces, and I will have different pricing for those different marketplaces, and I don't necessarily want all of my customers to know the pricing that I'm offering to different companies. And so on the Hyperledger side, there's an effort to be able to provide private transactions and confidential contracts. Of course, security is key, and to be able to maintain the security and the cryptography that blockchain provides is important. to maintain that. Then also on the Hyperledger side, to be able to have a modular architecture. There are different components that come to play, and blockchain is really a collection of different technologies. And the Hyperledger lets you put different components in that function better for your particular use case. So you'll have a membership service, and there are different membership services that can be used, different ordering services. Kafka is the default in Hyperledger, but you can use your own ordering service to put the transactions in the order. Same with state databases. By default, the state database is just a key value store, but you can also use a CouchDB, or you can plug your own state database in. So Hyperledger really comes at blockchain from a very different perspective, and addresses some of these issues in a different way. As you look at some of the things that are inherent with an Ethereum or public blockchain, Glenn talked about cryptocurrencies and the exchange of value. When you get into an enterprise environment, it works a little bit differently. With accounting, there's a distinct difference between ownership and possession of a particular asset. And so the real-time kind of cash basis that functions on a cryptocurrency don't work very well for accounting transactions. And Hyperledger allows you to have the latency in a transaction that comes in accounting. So those are some of the unique things with Hyperledger. I've done a number of design projects implementing Hyperledger blockchains, and one of the things that's very helpful as I begin those projects is to understand that there are really 4 constructs that you want to use to evaluate use cases as you put them onto Hyperledger. And the constructs are assets, members, transactions, and events. And as you go into any scenario where you're going to implement a Hyperledger blockchain, you're first identifying the assets, the real world assets or abstracted assets that you will be tracking. And in a Hyperledger environment, you can define the structure or the model of those assets. So they can be very simple, or they can be very complex. But understanding the asset that you will be operating around is really key. The next step is to understand the members who will participate in the transaction. And in a Hyperledger environment, because it's permissioned, you have to be invited to be a member of the network and be provisioned into the membership services. But understanding who all the different participants are is really important, and you can have many members invited to a network, but also have within that network what are called channels, where you can segregate private transactions. So even though you're a member of a Hyperledger network, doesn't necessarily mean that you'll have access to all the transactions and all the assets that are recorded on that blockchain, because they can be segregated with access control lists and also with channels. The next construct is transactions. Glenn talked about smart contracts on the Ethereum side. In Hyperledger, the smart contracts are called chain code, and chain code allows you basically to codify workflow between parties. So if you think of an ERP system as an enterprise-centric application, what blockchain allows you to do is to elevate that application from the enterprise to the ecosystem. So I have one application that's running across my entire network. All of my members, or all the companies that participate across that network or that value chain, are provisioned as members, and the smart contracts or the chain code is the logic that governs the interactions between the different members. Transactions are chain code that are initiated from a member into the blockchain environment, and then the flip side are events, and those are chain code that are initiated by some event that happens in the blockchain that then pushes back out to the members. Let's go on to the next slide there, Glenn. I'm not going to get too deep into this just because there's so much, but one of the things to understand about Hyperledger, in order to scale at an enterprise level, different nodes in the network can be segregated to do different tasks. So not every node has to do every task. And there are the concepts of submitters and endorsers, consenters, and then committers are those that are actually ordering and writing the transactions to the blockchain. Those tasks can be segregated so that the entire network can run more efficiently. Different nodes within the network will interact with each other through the chain code. Chain code does not have to be instantiated at the network level. Chain code is instantiated at the node level. So that's another level of security in a Hyperledger environment. If I have a particular set of code or particular smart contract that I have established between two members of the network, that chain code can be established or instantiated just on those nodes. And so only those nodes know how to interpret the data that's stored in the block on the chain. So I can have members that are part of a network and may actually even be able to see a node but not be able to interpret it because the chain code is not instantiated on their node. Unlike Ethereum or a public blockchain where the miners provide the infrastructure on a public or a private blockchain like Ethereum, the members actually host the nodes. So infrastructure is provided by the members. It's not provided by miners, and it's not the world computer, but it's actually built by the nodes having hosting the software on their own hardware. Let's go on to the next slide there, Glenn. As you begin to work in Hyperledger, there are a number of tool sets that are really key, and there are different projects that are contributing these tools to be able to interact with the Hyperledger blockchain. A couple of them that I think are really key to know about. First is the SDK. Interactions with the blockchain are done primarily through SDK or API calls. Right now there are 4 different SDKs for different languages. Node.js is kind of the native SDK and the one that's the most mature. Second to that is the Java SDK. There is also effort now to create a Python SDK and a Go SDK, although those are not quite as mature and not quite as rich in functionality. But those allow you code level interaction with the blockchain to be able to set up components of the network, as well as to be able to invoke the chain code. One of the Hyperledger projects that's underway right now is Cello. Cello is a relatively new project that's still in its infancy, but it's a tool that gives a graphical interface for spinning up the nodes and the members of the environment. Without Cello, it's all script and all script based. One of the tools that I'd really like to talk about is Composer. If you haven't dealt with Hyperledger or blockchain before, IBM has released a tool called Hyperledger Composer. There's actually a tool called the Playground. If you really want to understand Hyperledger and even blockchain, how it works, I would recommend that to you. It allows you to interact in real time through a very simple GUI with a blockchain environment and helps you understand all the different constructs that exist in Hyperledger and how to interact with them. There are a number of other projects that I just mentioned that are starting to be built out to flesh out the functionality of Hyperledger. But Composer, I think, is one that's really key and that will really help someone new to the space understand Hyperledger and how it works. And I think that's it, right, Glenn? That's a really quick rundown. Is there another slide after this? I think that was all of them.
No, it's
okay.
Yeah, so into skill. Thanks, Ken. And Ken has become quite an expert in this. He's built many proof of concepts and applications, and he has become our definite resident expert in Hyperledger and also very savvy in Ethereum. So thanks, Ken.
Yes.
So I want to spend just a couple of minutes and go over just our experience and skills and process and how it may be a little bit different than what you would normally run in an organization developing blockchain applications. And so it's one of the key things is having a solution architect. I mean, someone like Ken or we've got another person who really understands the blockchain technology, has a really good understanding of what blockchains do extremely well and what you need to complement in some kind of another type of environment. So it's good to have we call them a software architect, but you can also call them a solution architect that can model what you do on the blockchain versus what we call modeling off blockchain. And then it's really important, just like a good data model in a relational database or on MongoDB or a NoSQL database, you really need a good data modeler for the blockchain. Again, there's attributes just like there is in a database. There are smart contracts, the equivalent of stored procedures. And so it's important to make that trade between, what kind of computing you do on the blockchain and what is needed on the blockchain to show, in the case of Ethereum, the rest of the world that you have very solid ways to manage currencies or other types of contracts. So put the same emphasis there that you would on a relational data modeler. You do it well, you get higher performance, you get lower cost. You don't do it well, then you get lower performance and the cost can go through the roof. So in the public blockchains, it's all open source, and so transparency is it's the advantage, and so it is the spirit of the blockchain. Quality is also extremely important. And so the way we go through quality is we go through our normal development cycle where we develop both on-chain and off-chain, develop smart contracts, and then we have third-party auditors. And so there's a whole set of companies out there now in Ethereum and that will do code level audits. They can do it at Selenium level and validate the Selenium, or they can go down below that and actually do it at the bytecode level. If you're handling lots of financials, and a hack could cost, you've seen some of the hacks in blockchains and how much money they cost, $50 million, $100 million, $200 million. You have to invest in quality. You have to invest in making your code, solid. Financial institutions have done this for years, in their systems, but this is a different breed. This is open source. Your smart contracts are open source. Everybody can see it. If there's a bug, somebody will find it. The second way to do this is to have what's called bug bounties. And so you basically offer money, or in our case, coins, Bitcoin, Ethereum, Sweetcoin, and in the case of Sweetbridge, you offer bounties for people that find bugs in your code. They can find it in a running in a test system, or they can look at your open source and go into your GitHub or Bitbucket in our case and look. And as they find bugs and file bugs, you reward them with a coin, or in some cases money. So it's really important to have this as part of your process. In addition to a standard course. Yeah.
So Glenn, we're pretty much, and it looks like you're pretty much the end of your slides anyways. We just got 1 minute, so let's do a little wrap up, and we'll have to take questions offline for remaining questions.
Sure. Yeah, I apologize. So just a quick on Sweetbridge. I mean, we're essentially we're taking leveraging blockchain and taking blockchain into the supply chain. So blockchain has typically been developed for fintech, but now the newer breeds of blockchain have provided provisions for building other types of applications. Sweetbridge, most of us come out of the supply chain world, and so that's what we're doing. We're doing it through alliances. My team is building the underlying protocols to go up through settlement, and then we have a financial aspect, and then we have supply chain experts. So that's what Sweetbridge is. Do you want to run through?
Yeah, so let me just quickly introduce Synerzip to those audience who may not have been aware of us. So Glenn, if you can just go to the next page. So for those of you who are not familiar with Synerzip, we are a software development, co-development partner, often with clients and partners like Sweetbridge. We're working with them and other such companies. Glenn, if you can go to the next page, I'll just quickly hit the main highlight for us as we get involved sometimes in very early stage in the MVP development and often a little later stage to help accelerate the product roadmap for our technology roadmap for our clients following good agile practices. So reach out to us if you want to talk more about your software development needs or in general or specifically about what we covered today on the blockchain, and you're trying to build a blockchain application. We'll be happy to take more questions. I think with that, let's respect the time box we had for 1 hour today. And if we can just bring up the last page to wrap up, let me just promote the upcoming webinar. In a couple of weeks, we're going to take another topic on deep learning, evolution from machine learning to deep learning, and we'll have our co-founder and CTO Vinayak Joglekar cover a case study of that with some real details. So stay tuned for that email announcement. And thank you all of you for attending, and thanks Ken and Glenn for covering this topic. I know this was rushed for us, but still very valuable.
Thanks for the opportunity, Hemant. We appreciate it.
Great to be with you.
Thanks, guys.